Okay, this is section 15.2, heat. We're going to talk about heat of reactions today. Okay, so we're going to talk about a calorimeter, what that is, how it's used to measure energy absorbed and released. We're going to explain the meaning of enthalpy and what that means and enthalpy changes in a chemical reaction and processes, pressure, force applied per unit area. I'll go over all this vocab, right? The main idea here is we're going to talk about enthalpy changes for a reaction is the enthalpy of the products minus the enthalpy of the reactants. And essentially, enthalpy, you can um, substitute the word heat. Heat and enthalpy go together, okay? So a calorimeter is an insulated device used for measuring the amount of heat absorbed or released in a chemical process or reaction. So this is a fancy bomb calorimeter because it's made out of a cylinder that is pretty substantial, so it doesn't um, break or come apart when a reaction happens inside of it, right? So we have some water in here. So we put a reaction inside this little container in here. Then we measure how much the water heated up. Okay, so we're figuring out, okay, we know what water is. We know everything about water. So if we measure how much water heated up, we know how many um, joules of energy were released or absorbed, that how much the water heated up or cooled off, and then we can figure out how much energy was released or absorbed during the reaction. So sometimes the reaction needs a little help to get started, so that's why they have these ignition terminals here to help get it started if it needs to in that case. Okay, so a little practice problems. We did one similar to this on the last section. But these calorimetry things, they always use the Q equals Cm delta T. Okay, so for this one, like as usual, we need to pick out from the problem a piece of metal with a mass of, so the mass, that's our grams, right? The 4.86 is going to go here. Absorbs 256, and the J is joules, so that's our Q when the temperature is increased by 182 degrees. So that doesn't mean the temperature is 182. The temperature went up by 182. So that's the delta T. Okay, so we got everything here, the joules, the grams, the delta T. We're looking for the specific heat. Okay, so we rearrange everything in this equation. So C equals Q divided by M times delta T. Plug in the numbers, right? 256 for the joules, 4.68 for the grams, 182 for the delta T. And you get 3.01. Okay, so if we are curious to see what metal that would be, you can look it up on a chart. Okay, just happen to have one right here. So looking down this chart, which metal would it be? Okay, so going down, the chart is in numerical order, so go down here. So strontium looks like it has the same same specific heat, so that metal is probably strontium. Okay, so another problem that we haven't done an example for yet is what's the final temperature? Okay, so these require, it's not any harder than the other ones, but it requires a little bit of extra thinking here at the end. I'll show you how that works. So it's this typical problem, right? They give us the grams. It gives us how many, in this case, kilojoules, K joules. So we got to be careful about that. And initial temperature of 30 degrees C. And it gives us a specific heat for ethanol. And what's the final temperature going to be? So this is the initial temperature. It wants us to find the final temperature. Okay, so this equation doesn't have a final temperature in it, but it does have a delta T. So that's what we need to find here. We need to find out what the temperature change was from this initial 30 degrees, okay? Since it absorbs this much energy, we know that the new temperature is going to be above this. So whatever our delta T is, we have to add 30 to that to get the new temperature. So these are the things we know. We know that's kilojoules, but we got to change it to joules by multiplying by 1,000. At 2.44 grams, 2.44 for the C is fine. The 124 grams, that's good. So again, I like to rearrange the equation to get the variable I'm solving for by itself. So this would be Q divided by C times M, okay, which gave me these numbers plugged in here. And I got a little over 5 degrees. Okay, so what am I going to do with that? That's not the final temperature, right? That's the temperature change. So to figure out what the final temperature is, and this delta T equals the final temperature minus the initial temperature. So if I plug that in, I get 30 degrees for the initial. So to figure out the final, I have to add 30 to both sides, and I get 35.2. You could also figure that out in your head, right, by knowing that since it absorbed energy, that the new temperature was going to be 5 degrees more than the initial temperature, which is be 35.2 degrees. Okay, thermochemistry and the universe. This is what we're going to talk about in the rest of this chapter, a lot of thermochemistry stuff, but it's not that bad, so don't get intimidated by that name. We're going to talk about the system. Okay, that's a specific part of the universe. So the universe is everything, but the system, when we talk about that, that's the reaction that we're talking about, that we want to study. We want to find out the heat for that is released or absorbed during that reaction. So this is the system, the thermochemistry system that we're studying is the reaction that we're looking at. Everything else that's not part of the system is our surroundings. Okay, and the surround. So the universe is a system plus the surroundings, right? So put it here a little simpler. Surroundings are everything else other than the system in the universe. Okay, chemists are interested in changes in energy during reactions. Okay, so changes in energy means changes in heat, and this they call these enthalpy is the heat content of a system at a constant pressure. So we have to have a constant pressure, otherwise there's too many changes that can affect the heat. Okay, the enthalpy in parenthesis heat of reaction is the change of enthalpy, the change in heat of in a reaction, and it's symbolized by this delta H, and the RXN stands for reaction. So the change in heat in a reaction is the final heat minus the initial heat, or more often we use this one we have in red, where the enthalpy of reaction, the heat of reaction is the heat of the products minus the heat of the reactants. Okay, so enthalpy changes for exothermic reactions are always negative. Okay, so an exothermic reaction is one that gives off heat. So it has reactions, the reactants create products, and there's a lot of heat given off. Okay, that's an exothermic reaction. Energy leaves that reaction system and flows to the surroundings. Okay, so from the system's point of view, the heat left that system, so the change in energy of that system, it had heat energy, had a reaction, then after that reaction it had less energy, less heat than before because some of that heat went to the surroundings. So that's a negative delta H. The opposite thing happens in an exothermic reaction. Exothermic reaction is a cold reaction, right? It has to take energy from the surroundings to make that happen. So that means that it had more heat energy after the reaction happened than it did when the reaction started. So that's going to be from the chemical reaction point of view, it has a positive change in heat, delta H. Okay, so a graphic, it looks like this, where we have the energy, the enthalpy, the heat of the reactants is up here. The heat of the products is down here. The enthalpy of the products is down here. Okay, so the products minus the reactants is going to be a negative number, and that heat that was in these reactants gets shipped off to the surroundings. It leaves this reaction system. Okay, the cold pack process is the opposite. The reactants are down here, the products are up here. Okay, so for the products to have gained heat, to gain that delta, that enthalpy, it had to take heat from the surroundings to make this reaction happen. So when it takes heat from the surroundings cool off, right? That's why it's in a cold pack. The surroundings get cold because this reaction is taking heat from its surroundings to give more heat to these products than we had for the reactants. So the heat had to come into this reaction system from the surroundings. That's why the delta H is positive. Okay, so we're going to do more with that delta H and enthalpy stuff in the next section, but that's it for this section. Okay, a little vocab review. The specific part of the universe you're studying is, that's the system. Heat content of a system under constant pressure, another vocab word. That's our new word for the day is enthalpy. Okay, so answer the questions down below on the web assign, and I'll see you guys in class tomorrow.